Hello, my name is Wen Xiaoxuan. I will explain a test and set simulation for mutual exclusion and briefly discuss the program output. The loc is represented by an integer variable. 0 means the loc is free, and 1 means the loc is busy. This is the test and set function. It returns the current value of the loc and automatically sets it to busy. Enquire uses busy waiting. If the loc is busy, the thread keeps spinning until it becomes free. Release sends the loc back to free, allowing another thread to enter the current call section. Each thread first acquires the loc, enters the critical section, and releases the loc after finishing. 5 threads share a single loc, which demonstrates mutual exclusion. From the output, we can see that only one thread enters the critical section at any time. Each enter message is followed by its corresponding exit message before another thread enters. Although the execution order of threads changes between runs, mutual exclusion is always maintained. In summary, this program demonstrates mutual exclusion using test and set and shows that busy waiting wastes CPU. Thank you.
Hello, my name is Huang Ziyu. I'm responsible for question 2, implementing a custom counting semaphore with first in first out fairness. And here's my semaphore. In my semaphore, I use an integer value for slot and a first in first out queue for waiting thread and wait notify for blocking instead of busy waiting. I add a atomic integer code in CS just to show how many threads are inside the critical section, and it should never go above 3. Then the thread lock. Each waiting thread has its own block object, so when I notify, I wake up exactly the correct thread. Then the semaphore is start as with value 3, meaning 3 available slots. Here is it. And now is the p-wait. In p-wait, I first synchronize on the semaphore object to safely check and update shared data like value and the queue. And if the value is greater than 0, the thread takes a slot by decrementing value and enters immediately. And here's the case B. If value is 0, the thread cannot enter, so I enqueue it into the first in first out queue. And here's the block. After enqueuing, the thread blocks using wait, so it doesn't waste CPU time, and this is not busy waiting. The block the thread instead of the busy waiting. And when the thread is notified, it wakes up, increment in CS, and enters from the queue. And here we come to the V signal. In vSignal, the thread is leaving the critical section, so I decrement in CS first. And if there are waiting threads, I take the head of the queue using poll and notify the exact thread. That is first in first out fairness. And here's the poll. And if there's no one is waiting, and I just increment value to return the slot. And now it's task B. And in main, I create 5 threads and start them almost at the same time to simulate concurrency. And each thread calls pwait to enter, sleeps or simulate work in the critical section, then calls vSignal to leave. And finally, I use join to wait for all threads to finish, then print the completion message. And now it's the result. As we can see, thread 1 entered, thread 2 entered, and thread 3 entered. Then when the thread 4 is coming, it need to wait because the above is not to can be above to 3. And now thread 5 is waiting too. And after thread 2 is leaving the queue, the first in the queue is thread 4. So thread 4 entered, and thread 1 leaving, and the last the first one of in the queue is thread 5. So thread 5 entered, and thread 3 leaving, thread 4 leaving, thread 5 leaving.
Important topic in operating system, disk scheduling and disk strategies. We all know that disk read or write speed are significantly slower than CPU and memory speed. Therefore, how efficiently we organize the order of disk in or out requests directly impact overall system performance. The core objective of disk scheduling is to minimize the disk head movement. This is seek time. Next, I will introduce 4 common disk strategies. The first one is FCFS. The full name is first come, first served. This is the simplest schedule approach. It's processing requests strictly in the order they arrived with no reordering. The advantages are simple and no request starvation. And the disadvantages is inefficient. If requests are scattered across the disk, the head moved back and forth extensively, leading to long seek time and low throughput. FCFS is suitable for systems with light in or out load and few requests, or the snoring where fairness is more critical than performance. And the second one is SSTF. The full name is shortest seek time first. SSTF is an greedy algorithm that always selects the request closest to the current head position to process next. The advantages is significantly reduce average seek time and improve system throughput. The disadvantages is can cause starvation. If new requests keep arriving near the head location, requests farther away may never get serviced. SSTF is suitable for batch processing systems or moderate workload, where maximizing throughput is prioritized or granting individual response time. And the third one is SAAN. The full name is Elevator Algorithm. The SAAN algorithm moves the head from one end of the disk to the other. The servicing all requests along the way. Upon reaching the end, it serviced the direction and serviced the request on the return trip. The advantages is eliminate starvation because the head eventually sweeps across the entire disk. The disadvantages is uneven waiting time. If the request arrives just after the head passed to its location, it must wait for the head to travel to the end and return, potentially causing long delays. SAAN is well suited for high-load systems that require a balance of fairness and efficiency, such as general-purpose operating system. And the final one is Circularly SAAN. Circularly SAAN is an improved version of SAAN. The head move is only one direction. When it reaches the end, immediately return to the start without servicing requests on the return trip. The advantages are provide more uniform waiting time and lower variety in response time. And the disadvantages is the return trip result in some wasted seek time as no data is transferred during the movement. Securing SAAN is ideal for systems requiring predictable and bounded response time, such as real-time system or multimedia streaming. And finally, we will get the conclusion. Where SSTF offers high throughput, its risk of starvation is significant drawback. FCFS is too efficient for modern system. Therefore, SAAN and the Circular SAAN are generally preferred for handling heavy disk load.